Hi everybody, and welcome to the next video in our Unit 2 bonding video series, where we go a little bit deeper into covalent bonding. Before we do this, let's recap some things from last time where we were actually introduced to covalent bonding and saw how electrons could be shared between two atoms, both nonmetals, to form a molecule. We saw some very simple diatomic molecules like F2 with single bonds, O2 with doubles, and even N2 with triples. This video is going to go one step further and show you how to draw Lewis diagrams like these for these simple diatomics, but a little more complex. I have a set of 5 rules that I like to use to draw these molecules, which works pretty good most of the time. If you have a different way, that's fine, as long as whatever you do allows you to draw the molecules correctly. I'm going to show you how to apply these rules on a simple molecule, SO2. The first thing you do every time is determine the central atom and count the total valence. The central atom in this case is sulfur. It's the atom there's usually only one of. The 2 oxygens we put symmetrically around it, and the total valence here is 18. Step number 2 is to add in single bonds. You put in single bonds between each of the atoms. You have to remember though that single bonds each count for 2 electrons. So putting in 2 of them uses up 4 of our 18 with 14 left. The third step says give octets to the outside atoms first. That's the oxygens. This oxygen already has access to 2 electrons, so I have to give it 6 more. Same thing with the oxygen on the right. It also used up 12 of our 14, so we only have 2 electrons left now. Rule 4 says you give octets to the central atom last. Now I only have 2 electrons remaining, so I'm just going to give them to the sulfur automatically, and I have run out. Process seems to be over, except your final step should always be Rule 5 to check to make sure every atom has an octet. The oxygens are good, but sulfur, if you count, only has 1, 2, 3, 4, 5, 6. When you have this problem, you bring in an entire pair, let's see on the right hand oxygen, an entire pair from one of the outside atoms to make a double bond, and if you had to go one further, you could make a triple. Sulfur now has the 8 electrons it needs, and the molecule is complete. It should be noted that this is not the best representation for SO2. We're going to learn some things later on to alter these and make them even better, but it's a pretty good place to start. As always, this is a really important skill to have in chemistry, drawing these molecules, so I've given you 4 examples to try on your own. Pause the video, see if you can do it, and then hit play again to check your answers. Okay, let's take a look at these answers. Before we start, you should know I'm going to go through these pretty fast. If you're having a hard time keeping up and figuring out how to do this, an additional video has been added to the bottom of the Sophia tutorial. It's not required to watch, but if you need help, you need a slowed down version of what you're about to see, feel free to watch. Let's do NH3 first. The whole process for NH3 looks like this and gives you this. The thing to notice here is hydrogen looks like they don't have full octets, but they do. Hydrogen is so small it only needs 2 electrons to have that noble gas configuration. BF3, the whole process looks like this, start to finish. The thing to notice here is that boron appears to not have an octet. It only has 1, 2, 3, 4, 5, 6 electrons. Boron will almost always bond this way, and yes, you do have to know that. It's satisfied with only 6 electrons around it. NO3 minus 1, a polyatomic ion, looks like this, the whole process all the way through. That minus 1 means you have to add in 1 extra electron to your total valence. At the conclusion, it looks like this. You should end up making a double bond around one of the oxygens, either here or there. Also notice the brackets with the charge outside is technically the proper way to note a polyatomic ion. Finally, BRF3, start to finish, looks like this. The exception here is that bromine seems to be surrounded by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons. That's called an expanded octet, and it's okay. You can make those whenever you have to. Finally, we should point out that when you draw these Lewis dot structures, they're pretty good at representing how electrons are distributed within a molecule, but you should be aware they're also pretty bad at representing molecules in other ways. What I mean by this is everybody would probably draw the Lewis diagram for H2O to look like this. However, that's really nothing what H2O really looks like. It actually looks more accurately with this bent shape, and you could even represent it like this or like this. Point being, there's lots of different ways to represent molecules, and there's different reasons for each type that we'll learn about in the rest of this unit. That concludes our video. Thank you for watching. Please enjoy the wrap-up to follow.